Okay, so in this lesson, we're going to look at the Riemann sum and have this definition for a definite interval. So we did this in the last lesson. So we find the right Riemann sum approximation for the area bounded by the function e to the x between 1 and 3 and the x-axis with 4 equal subdivisions. So we go through our process here. Let me just go ahead and show it to you. We've done this already. So start off by graphing the curve between 1 and 3. You're going to do a right Riemann sum, so I'm going to cut this up into 4 equal subdivisions. So from 1 to 3, every half. And I'm going to draw the rectangle going up to the right side, touches the curve, and then over towards the left, just like so. So there's my rectangles. We can see clearly that it's going to be an overestimate. I can determine the length of each interval by taking the delta x is equal to b minus a over n, where n is 4. And you figure that out, and you get the spacing to be 1/2. Each of these little values in here on the right are important to us. We're doing a right Riemann sum, so I need that value, that one, and that one. And so those numbers are 1.5, 2, 2.5, and 3. So taking those values and finding the width for all of them is 1/2. So we have the 1/2 out front, and then the heights all added up, and we get our approximation for this area. But the real question is this. That's fine for an approximation, but what happens if we increase the number of rectangles? How much? Well, more. How about a lot more? How many can I put in there? Okay. Well, if I keep doing more and more and more, then what I'm getting a better and better and better estimate. Okay. The more rectangles, the more accurate my estimate. When we have some n equal subdivisions, the Riemann sum can be represented by this expression right here. See, very similar. So the change, so that the width of the rectangle, that's the delta x, and then the height at each one of those locations where we're taking our height value. Shortening this up into a summation notation, we get this representation right here, so it makes it easier to write all that. It's the sum of all the areas of the rectangles. This is the width, this is the height, right? F of x sub I is a height going from 1 to n. One rectangle up to as many rectangles that I want. So that is a representation of a Riemann sum, okay? Now, what if I take it to the point where I have an infinite number of rectangles? So to do that, we have to take a limit. And so that is our definition of a definite interval. As the number of subintervals of n increases so that n goes to infinity, the approximation becomes the actual area under the curve. If I take the limit as n goes to infinity of this, which is basically the sum of all the rectangles, so that just means I'm increasing the number of rectangles, then I can take this entire expression right here and write it in this fashion, which means the same thing. This now means the actual area under the curve. This is the lower limit, the upper limit. This represents the height of the rectangles, and this represents the base length of the rectangle. Okay? But when we do this, we have a function itself, the e to the x, as the function right here, because that's where the heights are determined. And so what it basically is telling you is I'm going to take the height of every single rectangle of every single point possible between 1 and 3, because we're going to infinity. Okay, so that's why this notation is changed. You're not physically going to go and find the heights anymore. We're going to use the function and the integral representation to help us do this. Okay, so let's take a look at some examples here. So we're going to be changing between the limit of a Riemann sum and the definite integral. So I have an example I want to express with you. Okay, so express the limit of the Riemann sum as a definite integral, starting with the lower limit at 0. Okay, and so I have this right here. I didn't write it up in here. I forgot to write it. So it is the limit as n goes to infinity of the summation I going from 1 to n, and I have 9 times x sub I squared minus 2 times 2 over n. So what would this be? And so part of what we're doing in this lesson is learning how to go from something like this to the integral representation. Okay? So we want to have an integral for this thing, and we're going to have our stuff that's sitting over here. We got to figure out what we're going to put in here. Well, the lower limit, I know they gave it to me as 0, so I know I'm going to start at 0. So what would be the upper limit? Okay, well, the upper limit is based off of this expression right here. The change in the x is b minus a over n, and that is that expression right there. So that has to be 2 over n. So from this expression right here, knowing that a is 0, I now can write this as b minus 0 over n equals 2n over n. And so then that tells me that b must be equal to 2. So we're going from 0 to 2. Okay? The x of I becomes the x. Okay? So delta x becomes that, or that becomes delta x, which becomes the dx. Okay? And this becomes the x. So if I take that and put it over in here, I'm going to get 9 times x squared minus 2. And then this becomes our dx. And that is our definite integral. Okay? Let's look at this one. Tilt it down just a bit, and I got to zoom in just a hair. Okay? Write as a definite integral on the given intervals that I have right here. So we're going to write this thing out. Okay? So for the first one over here, well, that's my A, and that's my B, correct? So I'm going to integrate from 0 to 5. This expression over here, that's going to become dx, and the xi is going to become x. So this is simply going to become, in parentheses, x squared plus 3 dx. And then from this one over here, we're going to do the same thing. This time we're integrating from 2 to 6. And nothing else changes from this part of it. So we get, again, x squared plus 3 dx. Okay? Here's another one down here. Okay? So how do I do this one if I'm going to have a equals 0 again? So it's the same kind of problem we did up in the original one. We have to find the b value, which we don't know. So I know that delta x is equal to b minus a over n. A is going to be 0, and this has to be 7 over n. Okay? And so then this leads me again to say that b must be equal to 7. So I know that this is going to be an integration from 0 to 7. The x of I is going to become x. That's going to become dx. The 4 is here for the ride. And so we end up with basically 4x to the 5th, and then dx. And there it is again. Okay? So let's take a look at what's next. So in this one, I have this equation, this example right here. Sorry, you couldn't see it. We're going to use a right Riemann sum with 2 subintervals to find an approximation for this, where g of x equals that. Okay? So what we're going to do now is we're going to put it and find this approximation thing. Okay? So how do I do that? Well, the first thing you should do is draw a picture. Okay? You have literally this right here. We're going to integrate from 1 to 3 of g of x, which is this quantity right here, dx. So we need to graph that between 1 and 3. So you just need a quick sketch of it. Here's 1, here's 3. If I plug in 1, okay, I'm going to get 3 squared, which is 9. I plug in 3, I'm going to get 5 here, and square that's 25. So I literally have something that looks like that. Okay. A subinterval, 2 subintervals means I'm going to have that. A right Riemann sum is this rectangle going over this way for an approximation. Okay. So our delta x is going to be 3 minus 1 over 2. This gave me the width of 1. That's how I knew it was going to be a width of 1. Okay. And so what is my approximation going to be for a right Riemann sum? It's the width times the height here, which is 2. So this height right here, well, that height is g at 2. And then this height, which is g of 3. Okay. So this is going to be g of 2 plus g of 3. And then we can figure those out by our numbers over here. And we're going to have 1 times at 2, I'm going to get 4 squared. At 3, I'm going to get 5 squared. And we can work this out right here and get the answer 41. So there's our approximation right there. Express this definite integral as a Riemann sum. Okay, so we went from the integral to the Riemann sum. So now we're going to go from, we went from the Riemann sum to the integral. So now we're going to go in the other direction. So this expression up here is 3 to 8. I don't know if it's hard to see that or not. And we have 2 times the quantity x minus 3 to the third power dx. And so we want to change that over. We have the b and the a right here. So we need to find the delta x, which is b minus a over n, which means we have 8 minus 3 over n, or 5 over n. So we're going to use that expression in our problem. The x becomes x of I in our expression. And so we're going to have the limit as n goes to infinity of a summation. I is going to go from 1 to n. And then we need to find our expression, our f, and our delta x, which we have here. Our f is going to be, just write that expression again, where you get to the x, put an x of I to the third, and then our delta x. Oops, sorry. And that is how I can go back. Okay? All right. So let's look at this a little bit more before we go into this last question over here. I want to look at something over here, and so you can get a definite idea how to go about doing something. Let's see if I can get that without it being so blurry. How do I distinguish between a left and a right Riemann sum? Okay, so this kind of helps, gives you some guidance on how to go about doing it. So let's write this expression as a left Riemann sum and a right Riemann sum. Let's walk through the process. The first thing you want to do is you want to find that delta x, just like we did before. And the next one is how we distinguish between a left and a right Riemann sum is this right here. Okay, so the x value, or x of I, the value x value to plug into the function for the ith rectangle. A right Riemann sum, that's going to represent that quantity, and this was going to be that quantity. See how this was an I and this is an I minus 1. So what we're doing here is this. Let's kind of use this one as an example. If I'm doing a right Riemann sum, then it's from the starting value a, okay, plus whatever that width is, and that's where I need to go up to. Okay, so if it's a right Riemann sum, a is the starting value. From the starting value a, so I can get them both in the same frame. From the starting value a, I need to add that change. Okay, and that's what it means to put up here. For a left Riemann sum, okay, I need to basically come backwards to that. Okay, so x of I is going to be like for example, you're standing right here. I need to go from A and add 1 less than there. So how do I get back to here? So that's how that kind of works. It's like you start at A, you go over to here, and you come back 1 to get to the left of this rectangle. This is the width of the rectangle, and so I'm over to here, and I have to go back to here to get that left endpoint. So that's how that kind of lays out there. Write the limiting summation with this and this, replace those values right there, and let me go ahead and show you how this kind of lays out. All right, so you can see how this is done. So let's look at this example right here. Kind of walks you through the same problem here, showing you how to do both of them. So here is this, okay, and by definition we have that, okay, and so there's the delta x. For the right, it's going to be x of I is going to be 0 plus I times that quantity right there, or that. Okay. If it's a left, then I'm going to start at 0, and I'm going to do this quantity, and that gives me that. So that's kind of like the difference between the two. All right, and then I come over here and I replace those values in here. So delta x gets replaced with that, and x of I gets replaced with these quantities right here. So they'll use these on the test, and so you want to make sure that you're kind of aware of how to go about doing this. So let's walk through an example of this. I think it's this example right here. Yeah. Let's kind of walk through one of these things and see if we can't get this one down. So we want to write it as a limiting right Riemann sum. So we have b minus a over n, which gives me 7 over n. Okay. So what we're doing here is we're trying to find out what value I'm going to plug into the function to get the height. And so it's a little bit different here. I'm going to plug in whatever these x of i's are to do it. Down here, I'm actually finding a value of kind of like n that does it. And so that's what we're trying to do. Trying to actually find that expression for that term over there based off of our starting point. So x of I is going to start at -2, and I'm going to, every rectangle from here is -2 plus whatever the next thing is going to be. And let me see if I can explain that a little bit differently. So here's -2. Somewhere I have these other rectangles. So this rectangle right here, this one right here, this spot on the, not rectangle, but this mark on the x-axis, how far is it? Well, it is that distance right there. And it is interval number 1. Okay, so this is interval number 1. So that's what I'm going to put here. I'm going to put some I, and then it's going to be 7 over n. So it's the nth one here. Let me put it differently. Get the I out of there. Anyway, how many intervals we have? It's going to be some fraction right here. So it's going to be -2 plus that fraction, and then negative this number plus that same fraction again, and then again, and then again, and then again. The I here is kind of like a counter, right? And the last number over here is 5. That total distance here is 7. So when I put in every single rectangle, n is going to be however many they are, okay? Then I'm going to get a distance. This right here is going to turn into, this whole thing is going to turn into the 5. That's basically what it boils down to. Ask me questions if it's confusing. It's kind of hard for me to explain what I'm talking about clearly. So let's just go ahead and write this out so you can see how it's done. We have our summation. This is all very standard right here. And I have a square root, x of I plus 2 delta x. So we start with that. Then we're going to change those out. Okay? X of I is going to get this quantity. Okay? And delta X is going to get that quantity. So this is going to be equal to the limit as n goes to infinity of the summation. I is going to go from 1 to n. And we have our square root. And then those values are going to be a -2 plus 7i over n. Plus 2, don't forget that one. And then delta x is 7 over n. Okay? And so then these notes in here, you can clean this up just a little bit. And so our final answer here is going to be I equals 1 to n. In here, I'm going to get 7i over n times 7 over n. And so that's how it could be expressed on the AP exam. So they'll tell you that you have a right Riemann sum. They'll show you stuff like this, and that will help you figure out what's going on in the other stuff. They'll give you more information like this. They'll say which one could be a Riemann sum, right Riemann sum, and you'd have to go and find this one right here or this one right here. So they could give you that one or they could give you that one. Okay? If they wanted to talk about a Riemann sum, they'll do that one because that's the definition. If they want a specific right Riemann sum, then they're talking about this. And so that's kind of what the whole point of this exercise here was about. We'll practice more of this together in class, and that ends this video.